Welcome to Electrochemistry. This is part 3, and I am Ms. Bedrosian. And we are looking at a battery, the kind of battery you might buy at the grocery store. Oxidation takes place at the anode. Yes, it has an anode, it has a cathode, and there's a paste in between it to allow charged ions to move. Remember where oxidation takes place, reduction. This is gaining electrons. It's at the cathode center, which is the cathode. And the electrons are moving from the anode to the cathode, even inside a little battery that you buy. Works exactly the same. Sometimes we use something called line notation in a book, and this basically puts everything happening at the anode on one side and everything happening at the cathode on the other, with a double line between them. Remember, so oxidation on one side, reduction on the other side. Oxidation is loss of electrons. Reduction is gain of electrons. Sometimes, however, we don't have a solid participating in the species. Sometimes it's an ion becoming a differently charged ion. And in this case, we use a non-reactive solid or conductor, such as platinum, can be used. So let's look at an example. Oh, we have a little Energizer bunny. The cell potential will always run spontaneously towards the right, in other words, towards products, because it must get a positive cell potential, must be positive. And that's our voltages. So looking at an example, if we have silver plus 1 electron, we get silver solid, and that's 0.80 volts according to the back of the book. We could have Fe3 plus an electron yields Fe2 plus, and that would be 0.77 volts. However, they both can't be reduction. One of these has to run in reverse. If you're going to put them together, they both can't be reduction. So what will actually happen? Which one will switch? Which one should we reverse? Well, reaction 2 must run in reverse because the cell potential must end up to be positive. So that's the one that has to switch. So electrons will flow from Fe2 plus to Ag plus. So oxidation will take place at the iron 2 plus, and reduction will take place at the silver plus 1. It will pull the electrons from the iron. How would we write this? Platinum, solid, and then we'd had Fe2 plus would end up as Fe3 plus, that's the change, double line. Silver plus 1 ends up as silver solid. We have to have the platinum because the iron remains as an ion both times, both ways. So the cell potential, EMF, electromotive force, is the same as a volt, which is the same as joules per coulomb, which is the same as work over charge. And in this case, what we are looking at is negative work per Q. Why is it negative W? Well, work is looked at from inside the system. If it's leaving, then it's negative W. The cell potential is positive. Work would be negative. Some energy is always wasted, so we never get the calculated cell potential maximum, by the way. Now, under standard conditions, let's see how this relates, according to the little giraffe. How does it relate to Gibbs free energy? How does this relate? Well, of course it does relate. So under standard conditions, we have a handy-dandy little equation. Delta G prime is equal to negative NF times the cell potential prime. That E should be rounded. My program won't let me do that. It's kind of like an epsilon E. All right, here's Faraday's constant, 96485 coulombs per moles of electrons. And we're going to take a look at this. The maximum cell potential is directly related to free energy differences between the reactants and the products. Absolutely. And a positive cell potential has a negative delta G, which is required for it to be spontaneous. So for this to just occur when you connect them, you have to have a positive cell potential and a negative delta G. Looking at this example, Cu2 plus Fe yields Cu plus Fe2 plus. Write the half reactions. The reduction half, Cu2 plus 2 electrons yields Cu. The oxidation half, Fe goes to Fe2 plus 2 electrons. And now look up their voltages, their cell potentials, please. And for the first one, that would be 0.35 volts. This next one is a positive 0.44 volts because we had to switch it because this is oxidation. You have to flip it all. Add them together and you get 0.78 joules per coulomb. Remember, J per C is the same as a volt. Now let's look at delta G prime. So we have that's a positive number. Delta G prime is equal to negative N times F times the cell potential prime. And plug and chug. It's 2 moles of electrons, by the way. Plug this in and you will get negative 1.5 times 10 to the 5th joules. That works out. And taking a close look at this, since delta G prime is negative, and the cell potential is positive, then this must be spontaneous. All right, here's an example. Cu2 plus Cu solid yields zinc solid plus Cu2 plus. And I have 2 questions for you. Question 1. Will zinc ions plate out on a copper strip? In other words, will the zinc solid appear? And 2, what's delta G prime? Here come the answers. Question 1, no, because that's a negative 1.10 volts. And 2 is 212 kilojoules.